Okay, so this is part 3 of lecture 1, and we're going to be looking at some basic numerical descriptors. I'm going to be introducing some ideas that some of you will be familiar with, some of you won't. Okay, the majority of it you'll have come across before. Okay, so some of this is a bit of a revision topic. Okay, so we're going to be looking at numerical descriptors. So these are numbers that help to describe data. And one area that people seem to get really hung up on is measures associated with something that's called central tendency. Okay, the central tendency really is average, so measures of average. Okay, and there are 3 basic measures of average. They are the mode, the median, and the mean. And I've said those in that order because that's really in terms of their complexity. Okay, the mode is very simple. Okay, and we'll be looking at the definitions associated with these through to the mean, which is a bit more complicated. Some other useful descriptors that we use quite a lot within SPSS, and we use them because they are important, and this is a term associated with percentiles. Okay, and this is we use this actually when we're looking at hypothesis testing. Effectively, we're looking at various percentiles associated with distributions, and also something called quartiles. And they can be used in quite simple contexts. Okay, they can use, a percentile is how far in terms of a percentage along a distribution of value lies. Okay, a quartile is the same sort of thing, apart from it's got a special measure associated with it, and effectively it chops the data up into quarters. So you could have a quartile 0, which means the smallest value in a data set. Quartile 2 is an important one because a quartile 2 is the median. Okay, but I'll discuss these a little bit more in detail later. And then we've got something that comes up quite a lot, and that is association with variation of data. And there are some basic measurements here that you will be familiar with, and some of them you may not be familiar with. Okay, the simplest one is the range. Okay, so we'll be looking at what is the range of a set of data. Okay, and then the next one along from range is really something called the interquartile range. The interquartile range is very useful because it gives us the middle section of the data distribution. And we'll also be looking at the term called variance and standard deviation. Now, often people will remember standard deviation but forget variance. The interesting thing is that standard deviation is derived from variance. So again, I'll be talking about that when we go through. And then finally, I've got something called the coefficient of variation. And the coefficient of variation is quite useful for initially comparing different sets of data. Okay. So let's look at some of these simple statistical models for measured variables. The mean. Okay, well, the mean is an hypothetical value which measures the arithmetic average of a set or a distribution of values. Okay, so, and what it is, it's a weighted value, and the way that we get it is we obtain this measure, the mean, population mean, when we're dealing with all the values in a data set, is represented by this Greek letter mu. Okay, where it says mu is equal to sigma x1, x2, and so on up to xn divided by capital N. Well, what on earth is all that? Okay, well, what it is basically this says add up these values and divide by how many you've got. It's as simple as that. Okay, now the median in the distribution, it's the particular value such that half of the data values are less than the median and half the data values are greater than the median. So in other words, it's the midpoint of the data set. Slightly different than the mean, okay, because we're not actually adding the values up, we're looking more of a location. Okay, so if we have 10 values, okay, then the median is somewhere between the 5th and the 6th value. Okay, and if we were doing this, practically, you'd say it's between the 5th and the 6th value. So I add those two values together and then divide by 2, and that gives me an approximation for the median. But if you've got an odd set of values, let's say we've got 11 values, then the median is the 6th value. When I talk about the 6th value and the middle value and so on, what I've got to do to start off with is put the data in some form of order. Because it does say in here, half of the data values are less than the median and half of the data values are greater than the median. Okay, so that's just indicating that that capital sigma means to add up to sum the values. So if we look at the median and frequency distributions, here we've got the median could be very useful also in the case of frequency distributions. Look at the table below. It refers to the level of attendance shown by students at my statistics workshops in the past. Okay, so what I've got is I've got these workshops, workshop 1, 2, 3, 4, 5, 6, 7, and 8. And these are the number of people attending. Okay, so the first one, 8 people turned up. The second one, 12 people turned up. And third one, 15 people turned up. Fourth one, 22 people turned up. There must have been a registration going on that week. Okay, the fifth one, 18 people turned up. The sixth one, 10 people turned up. The seventh, 9 people. And the eighth, 6 people. Then we've got their cumulative frequencies. And the way that we get cumulative frequencies is by adding up as we go along. Okay, so first group, 8. End of the second group, 20. 35, 57. This is simply just by adding this value. Okay, so 12 plus 8 is 20, 15 plus 20 is 35, 22 plus 35 is 57, 18 plus 57 is 75, 10 plus 75 is 80, 85, 9 plus 85 is 94, and 6 plus 94 is 100. Okay, so you've got the idea. So the median will be an observation that splits the distribution into 2 equal parts. So in this case, n is 100. So the median will be between the 50th and the 51st value. So we need to find the class that's got the 50th and the 51st value in it. Okay, and if we look at this, the 50th and the 51st observation among the students attended the 4th workshop. Okay, because this is from 35 up to 57. Okay, so we've got, it falls between the cumulative interval of 36 and 37. Okay, we can say then that half or 50% of the students attended the first 4 workshops, while the other half, or remaining, attended the last 4 workshops. Can't say which individuals, but what we're making up an observation. Okay. So simple statistical models for attribute variables. Well, I could have done this one first, and that is the mode is the simplest measure of average. Okay, and it represents the value that occurs the most frequent in a set or a distribution of values. And now remember, attribute means qualitative variables. They can be analysed by frequency counts with respect to terms such as quality diversity, which are nominal variables, or bigger and smaller, which are ordinal variables. Okay, so if you're doing the survey of the different colours of cars on the car park, you may find that red is the most popular car. So the mode of colour of car on the car park is red. So these are simple exercise for you to do. So Brian's got 17 colours. Here are their ages. Okay, and I've been very kind. I've actually given them to you in order. I've got 2, 3, 3, 3, 6, 6, 6, 6, 7, 8, 8, 9, 9, 10, 14, 15, 15. Okay, what's the mean? Add them all up, divide by how many you've got, and you get 7.68. What's the median? Okay, 17 cousins. Okay, so the midpoint is between the 8th and the 9th is, so we get 8th and the 9th. So for the median, you need the midpoint, okay, and the midpoint of 17, okay, that's an odd number, okay, so if you add 1 to it, you divide by 2, it will give you the location, okay, so if I add 1 to that, I get 18, divide it by 2, and I get 9, so I want the 9th observation, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and the mode is the most common observation in there. Now, we've got to be careful with the mode because the mode could be bimodal. Okay, so there may be 2 categories that have the same number of counts. Okay, there may be more than 2 categories. Okay, but if it's a unique mode, there'll only be 1 category that has the highest number of counts. Okay, and that in this case is 6. Okay, very simple exercise. Measuring differences, the sums of squares. The mean is an important statistical parameter as it enables researchers to obtain other useful parameters useful for describing data. Okay, now I'm using this word parameter. Okay, now within this word that we're looking at, we're going to be looking at parameters and statistics. Parameters are values that are associated with population means. Statistics are values that are associated with samples. Okay, that's worthwhile remembering. Now the sum of the squares, it is the sum of the square differences, so that this is referred to as abbreviation SS. It's quite a common abbreviation. Okay, it's the sum of the square differences taken between all the observations of the distribution and the mean of the distribution. So I've got the first value, I take away the mean, okay, I square it up so it becomes a positive answer. Then I add on the next square difference and so on right through the data set, and that gives me SS, sum of squares. Fortunately, you don't have to remember this a great deal because SPSS will take care of this for you, it does this work for you. Now the variance by definition is the sum of the squares divided by how many observations you've got. Okay, and again this is a population value. Okay, so it's not a statistical value, it's a population value. And the standard deviation by definition is equal to the square root of the variance. Okay, so you can see that then standard deviation is actually equal to the square root of SS divided by how many observations you've got. For a population measure, it's different for a sample measure. Do you need to worry a great deal about it? And the answer is no, because SPSS will take care of it for you. Now, when we look at percentiles and quartiles, a percentile is a value corresponding to a specific percentage along an increasing ordered data set. And a quartile is the value corresponding to a specific quarter along an increasing ordered data set. So really, we've got quartiles, Q0, Q1, Q2, Q3, Q4, and they are equivalent to percentiles 0, 25, 50, 75, and 100. Okay, and you'll notice that the Q0 is equal to the minimum of the data set, so the smallest value of the data set. Q1 is a lower quartile, so that's 25% of the way along the data set. Q2 is equivalent to the median, which is halfway along the data set. Q3 is termed the upper quartile, which is 75% along the data set. And then we've got Q4, which is 100% along the data set. Okay, in other words, the maximum value. Okay, so quite easy to apply. SPSS will actually do this for you. It's pretty good. Okay, when we look at measures of dispersion, okay, so this is variation. Quartiles are useful when researchers wish to identify or investigate defined proportions of the distribution. Now, the range is a very easy measure of dispersion. Okay, and the range is the biggest value minus the smallest value. The range is a value that's associated with mode of the data. Okay, so when you have a measure of dispersion, you have a measure of average that goes side by side with it. The interquartile range represents the central middle 50% of the scores. That's between the two quartiles at either end of the distribution. Okay, it's the central section. And it's calculated by finding the lower quartile, okay, and the upper quartile. And the difference between them, that is Q3 minus Q1, is equal to the interquartile range. Okay, and the interquartile range, unsurprisingly, is associated with the median. Then we have variance and standard deviation. Both are measures associated with the spread of the data about the mean. So now we're talking about how is data spread associated with the mean. Variance is a measure in square units. Remember, SS squared divided by n. The standard deviation is a square root of variance. So in other words, it isn't in squared units, it's in standard units. It's in the same measurement as the original values. So if your original values were in centimeters, then your standard deviation is in centimeters. If your original variation and values are in kilograms, then your variance is in kilograms squared. Your standard deviation is in kilograms. Basic statistics relies more upon the use of standard deviation. This is why people often remember it more so, is because the stats that they've done is generally associated with standard deviation. Actually, the statistics they've been doing have been really population measures. More sophisticated techniques make use of the variance or standard error of the sample, and we'll look at these later. Okay. The use of the population standard deviation. When analysing data, a first step could be the analysis of the mean mu and the standard deviation sigma. Okay, just to confuse you, if you're not familiar with these characters, that's the lowercase sigma. Okay, so lowercase sigma means standard deviation. Okay, lowercase sigma squared means variance. Population, standard deviation, and population variance. Capital sigma means to sum up, to add up. Okay, a small value of sigma indicates that the data points, values within the variable, are not distant from the mean. In other words, they are quite close to the mean. In this case, the mean is a good representation of the data. Okay. A large value of sigma indicate that the data points, the values within the variable, are a far distant from the mean. In this case, the mean does not provide a good representation of the data. So rule of thumb is that you have your mean and your standard deviation. If your standard deviation is large, then the mean that you've got may not be a good representation of the data. So these conditions are useful in terms of research strategy and may influence researchers' decision. they do play an important part in research strategy because sampling theory is often applied within research strategy to determine how big a sample to use for means of research, such as how many questionnaires should be sent out and so on. And that is associated with getting validity and reliability within your data. Now, here I've got a distribution. I'll be talking more about the shape of the distribution and the type of distribution that's there. Okay, this is a bell curve shape. It looks fairly symmetrical, and it's been taken from a national retail company from data set from 2010, 2011. And it's a graphical representation of an attribute variable, age of customer. Okay, so we've got the age of customer varies from this data set, and it's bell shaped. It looks fairly symmetrical around the middle, okay, around 40. Okay, and we can see just below the age of 40 is the mean. Okay, it's not that symmetrical because if I look at the shape of this left-hand tail, it is slightly different than the shape of this right-hand tail. Okay, and we find that the median is actually just slightly larger than that. Okay, this tells me something about the distribution. It tells me that this distribution has got a skew associated with it. It says that this data, that because the median is larger than the mean, is skewed to the right-hand side. Okay, we look at the tails in terms of skewness, which tells me that it's got what's called a positive skew. It's only a small positive skew, but it's got a small positive skew associated with it. When we look at this household data from the same data set, the household income, we can see that this has certainly got a much greater skew than the previous set of data. Okay, and we can see that the mean is between 20 and 30,000 pounds income, and the median is shifted far further over to the right. So this is saying that if the median moves away from the mean, the further it moves away from the mean, then the greater the skewness associated with that data set. So here we've got another distribution of continuous. This time we're looking at continuous variables, and we've got the heights of adults 18 years and older. Okay, and the heights are in inches. Okay, and we've got that the data looks fairly symmetrical. Okay, and the height is somewhere between 65 and 70, the average height. Okay, so it looks around about 67.5 inches. Okay, the spread of the data is indicated by the standard deviation. Okay, so it doesn't indicate the whole spread of the data, okay, but it tells me if there's a number associated with it, it will tell us how close it is to that mean. Now here we've got children's heights and adults' heights. Okay, and don't worry about the distribution looking like they've got the same height in terms of the shapes of the curves. Okay, they're the distribution, they're the number of values that are falling within those areas, remember. Okay, so these two distributions, it looks like the average height of children is around 50 and the average height of adults is 67.5. Okay, so it looks like there is a difference between children's heights and adults' heights. But you can get very tall children and you can get very short adults. So you have these overlapping of the two distributions. Okay, and that lends itself to saying, trying to imply, is there a difference between these two? Statistically, is there a difference between these two? And we'll be looking at that later on in terms of what we call hypothesis testing. So these have similar standard deviations because their curves look pretty much the same, but they certainly look like they've got different population means. Here's another set of data. This is the height of individuals making up population nation X, and another variable of nation Y. Okay, and if we look at these two sets of data, okay, in terms of their distributions, again, they'll both look fairly symmetrical, okay, and they look like the average height is around the same, 67.5 inches. However, if we look at variable B, you'll see that it's flatter, okay, it's not as tall in the distribution, so it's not as peaked, it's flatter. Okay, which suggests that the standard deviation for variable B is bigger than the standard deviation for variable A. So here we have similar population means but different standard deviations. Now, describing the distribution of a measured variable. A statistical distribution for a measured variable can be summarized using three descriptions. It can be summarized using the center of the distribution, the width of the distribution, the symmetry of the distribution. And indeed, I've used those terms as I've described each of those distributions that we've gone through. Okay, now remember the center of the distribution, if you want to call it central tendency, is really referring to our average. Okay, so we could be using mean or we could be using median. If we're using mean, then the measure of spread, the measure of variation, is standard deviation. If we're using median, then the measure of spread that we want to look at is interquartile range, and that's the difference between Q3 and Q1. So here's a distribution where we can use the quartiles. Okay, so we've got a distribution of data. Okay, measuring the width of distribution, we can use standard deviation. Okay, remember this. You don't have to, when I say remember it, you don't have to remember it because SPSS will do the calcs for you. Okay, but just remember what it means. Okay, the interquartile range is the range over the middle 50%. So you could actually chop this data up into Q1, Q3. Okay, and the interquartile range is between Q1 and Q3. Okay, so it's just a number. You never write it down Q1 to Q3. You always do the subtraction Q3 minus Q1. Any range value is a number. It is not A to B. Okay, now moving on to describing a measured variable in terms of skewness. And again, I've been talking about skewness as we've been going through. Okay, measuring the symmetry of the skewness of a distribution. Okay, a negative skew is, you'll see that the distribution for negative skew is the tail on the left-hand side is much longer than the tail on the right-hand side. If you were to see the peak to be the center point and then have a symmetrical distribution in between, it's quite awkward to see, it's quite light, the color there. Okay, then this section here is indicating we have a negative skew. Okay, and similarly, this one here has a positive skew. Now, people often get this wrong when they look at data sets in terms of what is a negative skew and what's a positive skew. And the reason why is because we always think of skew as being leaning towards something. And if we look at this, this is leaning towards the right-hand side. Okay, which you might think if it's leaning towards the right-hand side, it's got a positive skew on it. It's wrong, and it's because it's the tail of the distribution that we want to look at. Okay, so intuitively, it's the opposite of what we think. Now, there are two standard measures of skewness that we can use. There are other measures as well, and SPSS gives these other measures too. Well, the two standard measures of skewness are the Pearson coefficient of skewness, which is 3 times the difference in the mean and the median, okay, divided by the standard deviation. Okay, and then we've got the quartile measure of skewness. A little bit more awkward, this one, okay, but don't worry about it. SPSS takes care of these things for us. And it is Q1 minus Q3 minus, in a brackets, Q2 minus Q1, and that's all divided by the interquartile range, which is Q3 minus Q1. So shapes of distributions, if the median is to the left of the mean, then it's got a negative skew. If the median and the mean are on top of each other, coincident, then it is symmetrical. Okay, and you'll find that Q1 and Q3 are at the equal distance either side of the median and the mean. And a positive skew is where the median is bigger than the mean. So median less than the mean, negative skew. Median same as the mean, symmetrical. Median bigger than the mean, positive skew. We can represent these using this little funny diagram at the bottom here. It's called a box plot, box and whisker plot, to give it more formal title. Okay, the box and whisker plot, SPSS is actually very good at doing these. Okay, and it does apply some rules, and I'll show what those rules are in a few minutes. Okay, so here you can see that the median is inside the box. That's this thick line here. The edges of these boxes represent Q1 and Q3. The left-hand side traditionally would represent the minimum. The right-hand side will represent the maximum. However, SPSS applies a different rule to it. It's a standard statistical rule, actually. Okay, and it goes beyond the basic of a distribution. It allows us to say that actually within a distribution can have points that come well beyond the limits of these tails that we see. Okay, and they're referred to as outliers or extreme values. So a symmetrical distribution, you can see that the median is in the middle of that box, okay, and these tails are the same length. A positive skew, okay, the tail is larger, the median is in the box, but it's pushed over to one side, okay. So the rules that SPSS adopts for this, when it plots a box plot. This is a box plot that I plotted within SPSS for some data. It doesn't matter what the data is, it's just a plot that it gave me. And you can see that it plots in the vertical sense. You can change the orientation if you want, but I'm pretty lazy. I try and keep everything defaulted as it is, okay, wherever possible. So generally box plots, SPSS puts them vertically. Okay, so we got our box plot, okay, and we can see that this box plot, okay, there's the median, that's the upper quartile, that's the lower quartile. So this is on a scale that's running from small to large, the vertical axis, okay. There's no real horizontal axis, but there could be if there were more than one category. So if we had some attribute variables in it, say I had gender, I'd have a box for female and a box for male. Okay, I may have them all together. So this might be gender all piled in together. Okay, and this might be, let's say, salary. Okay, monthly salaries or annual incomes. Okay, so what have we got? We've got the box, we've got the whiskers. Okay, and these whiskers are not representing the maximum and minimum values, they're representing cutoff points. Okay, and beyond those cutoff points, you have an area or a region that represents an outlier, and they're denoted by circles. And then beyond the outlier area is what we call the extreme value area, and these are represented by these stars. Okay, so there's the median. The interquartile range is the difference between this value and this value, okay, which is the length of the box. And then we have this rule of where does a value become an outlier. And the rule is that a value becomes an outlier if it's beyond 1.5 times the interquartile range from the upper quartile and the same from the lower quartile. Okay, and then there's a range passed on that, and that is 3 times the interquartile range. Okay, so the same sort of distance again as before. Okay, so if it's between 1.5 and 3 times the interquartile range, then it's an outlier. If it's 3 times the interquartile range or above, then it's an extreme value. Okay, and that's really a basic discussion on various numerical scale descriptors as well as some graphical description in there associated with basic statistics. Well, when I say basic statistics, I would say basic measures associated with populations. Okay, because I've not looked at any samples yet. So in summary, what we've done in this part is we've learned how the measures of central tendency and dispersion and how to calculate them. We've identified the difference between population parameters and sample statistics. Okay. We've discussed how descriptive measures relate to some important graphical representations, and we've examined the shape of distributions of numerical data.